Hi guys, John the Quant here. This is still week 5 of the Data Science Bootcamp that I'm delivering to all of you for free, and I also guide at the Community College of Aurora. Now, hopefully you guys just came from the video on supervised learning, and if you didn't, there's going to be a pop-up right over here to take you back to that video because you really should watch it. Now, this video is all about unsupervised machine learning, so let's go for it. Now it's time to talk about unsupervised machine learning. So when we were talking about supervised machine learning in the previous video from this week, we said that supervised machine learning was what happened when you knew the answers and you were training a machine learning model to return the correct answer. But unsupervised machine learning algorithms, they allow us to learn from data even when we don't have the answers. Now to me that kind of sounds like magic, but I mean, how can we learn if we don't have the answers, right? But it's going to make sense when you see it in action, okay? Basically, unsupervised algorithms let us answer the question, given this data, what other features can we deduce? There are a bunch of unsupervised algorithms, but they do largely fall into 3 categories. They are clustering, anomaly detection, and dimension reduction. So first, clustering, probably the most common form of unsupervised learning. Now, a clustering algorithm tries to assign your data into groups or clusters. And this is usually done with some kind of distance measure, such as the Euclidean distance, okay, which measures the straight line distance between points, like a triangle. Imagine a triangle, the distance between points is straight, that's the Euclidean distance. And it looks like this, but don't be too worried about this. It looks complicated, but this is the same as the Pythagorean theorem, okay? A squared plus b squared equals c squared. So c equals the square root of a squared plus b squared, right? So Euclidean distance is just a fancier term for the Pythagorean theorem, which is extended to have more than a triangle. So you can do this with 100 different sides of a triangle if you wanted, and it would work out, and that's the Euclidean distance. Next is the Manhattan distance, okay, which measures the stepwise distance between points. And it's called the Manhattan distance because it's kind of like walking through a city where you can't go straight. You've got to go up a block and over a block and up a block and over a block and up a block and over a block. But when you're calculating it, it's just the sum of the absolute value of the difference between each point. Sum of the absolute values. Very simple. The last one is cosine similarity, which measures the angle between vectors. And I think about this like the difference between hands on a clock. If one is straight up, pointed to the 12, and one is straight to the right, pointed at the 3, then the distance between those two hands is 90 degrees, right? So if you've taken like Calculus 3, I think was maybe the first time I saw this, then cosine similarity, this is just some basic vector stuff. The important thing to know is that it measures the angle between things like the hands on a clock rather than the distance between points. Angle between vectors rather than distance between points. So let's get into some clustering algorithms. The first one, the most common one, is called k-means clustering, and it's pretty intuitive. So first, you have to tell the algorithm how many groups you want. That's what k stands for, is the number of groups. Then you're going to randomly assign each observation to a group. Then you will calculate the center of each group by just like finding the average, right? And then you reassign each observation to the group with the nearest center. And then you just calculate the center of each group. And then you reassign each observation to the group with the nearest center. And then you calculate the center of each group. And then you reassign each observation to the group with the nearest center. And so on. You just repeat those 2 steps over and over until the groups stay the same. You'll usually see k-means clustering being done with the Euclidean distance. Actually, almost everything is mostly done with the Euclidean distance, but sometimes Manhattan distance comes in pretty handy. Cosine similarity is less commonly used unless you're working in some kind of NLP, natural language programming and processing or something. All right, so I have generated some fake cluster data. This is fake. You can see that there are 4 clusters that I made here. There's a little overlap between the fake clusters. Now let's do some k-means. From sklearn.cluster, import k-means. And then we're going to fit it with 4 clusters. In clusters equals 4. Fit it on just x. There's no y here. because this is unsupervised learning. There is no y in unsupervised learning. There's only x. So we fit it with 4 clusters because we knew that there were 4 clusters, and usually you don't know that. But let's see what comes out. So these are the clusters that I made, and these are the clusters that k-means found. And you can see they're pretty close, right? I mean, not everything is exactly the same. Look at this red dot here that's blue over here. This red dot here is blue over here. This blue dot here is green over here. But they're very, very close, very similar. However, like I said, we knew that there were 4 clusters, and in reality, you don't know how many there are. So let's see what happens if we fit it with 3 clusters. Well, these are the 4 clusters that we know exist, but if there were only 3 clusters, k-means thinks that they're these ones. And this is interesting because it's expanded these 2 clusters to take up more of the space. You can see that here, they kind of end there, but here they go all the way over there. That's pretty interesting. So, if we don't know how many clusters there are, how do we know how many clusters to make? There are really 2 methods that we use to figure this out. The first one is called the elbow method. So from here, I'm using a new package called Yellowbrick. Yellowbrick has a lot of really nice visualizations that are going to help us out. So from yellowbrick.cluster, I'm importing k-elbow visualizer. Now this is a visual designed specifically to help us figure out how many clusters to make with k-means clustering. And to use that, you call k-elbow visualizer. You have to give it a clustering model, and then you give it a range of k. So k here goes from 2 to 10. So it's going to fit a k-means clustering model with k equals 2, k equals 3, and so on, all the way up to 10. Fit it with doing visualizer.fit, and then you can show it. Ignore these warnings, they don't really mean anything. And here we go. So this line here is the Yellowbrick visualizer telling us what it thinks is probably the best number of clusters. It says 4 is the best. And we know, because we made the data ourselves, we know that 4 is correct. This is called the elbow method because usually when you do it like this, you'll see that it starts up high with lower number of clusters and it goes down and then it sharply turns off to the right, kind of like an elbow and like an arm, like a bent arm with an elbow. And at that point where the elbow bends, that is the best number of clusters. So here it's at 4. You can see that this elbow method worked really well on this data set where we already knew the answer. The second way that we determine how many clusters to make is called the silhouette score. And this one is in scikit-learn. So from sklearn.metrics, import silhouette score. And then I made this loop myself. We're going, k goes from 2 to 10 like it did before. And for each one of those 2 to 10s, we're going to fit a k-means model with that many clusters, fit it, use it to predict the clusters, and then get the silhouette scores for each one of those models, each set of predictions. And here, when we plot this, what you're looking for in a silhouette score is you want it to be as high as possible. Silhouette score should be high. So here we see a big spike where 4 clusters definitely has the highest silhouette score, so that is the best number of clusters. And once again, we know that 4 is the right number of clusters. So the silhouette score has worked for us. The second method of clustering we're going to talk about is called agglomerative clustering. And as far as I'm concerned, I think it's even simpler than k-means, okay? So for agglomerative clustering, first you find the 2 most similar observations, okay, the 2 with the smallest distance between them, and you stick those 2 together and you find the center of that pair. Okay, that's the average of the 2. Then you find the 2 most similar observations by finding the smallest distance between observations, including the center of that first pair. And then you stick the 2 closest observations together, and you find the center of that pair. And then you continue, and you find the 2 closest observations, including those 2 centers that we have, and you lump them together, and so on and so on and so on, until all of the observations are in the same clump, the same cluster. Then, if you want to split the groups into clusters, you pick a maximum distance and you cut any ties longer than that. So let's look at an example. From sklearn.cluster, import agglomerative clustering. I picked 4 clusters here. You don't actually have to tell it anything, but you can pick a number of clusters and it'll find that for you. So since I know that there's 4, we're just going to start off by finding 4, and we'll use fit underscore predict. For agglomerative clustering, you cannot fit and predict separately. You have to fit underscore predict at the same time. And here we go. This is what we know the answer is. And these are the clusters that the agglomerative clustering model found. Now, interestingly here, look at this. The purples kind of go off into the reds a little bit. And over here, it thinks those are the same cluster right here. Because they're so densely packed together right here, it's pretty sure that those are the same cluster, even though it's wrong. But, look at this. No, wait. I got it backward. Yeah. It kind of picked those up over there, even though it's wrong. And it says that these 3 blue ones are in the, say, the red cluster here, even though that's wrong too. So, it doesn't look, it looks like this agglomerative clustering maybe worked slightly less well than the k-means clustering before on this data set. But agglomerative clustering lets you do this cool thing called a dendrogram. So from scipy.cluster, I've imported hierarchy, and then you need to calculate the linkage by doing hierarchy.linkage on the data. And I used single linkage. Don't worry too much about what this means. There's a few options there. You can read about them in the scikit-learn documentation if you want. And then we did hierarchy.dendrogram on the links, and it draws this. So each one of these little tiny things that are too small for us to see is an observation, and they're all linked together with these lines. And as the lines get higher and higher up, that means that it's joining things that are farther and farther away. And as you can see, it really found 4 distinct clusters here. Very obviously 4 separate clusters, which we know is the right number of clusters. Now, if we hadn't known that there were 4 clusters, we could have just told it to make as many as it wants, and it would have produced the same dendrogram, but it wouldn't be in different colors. And then we'd have said, okay, let's cut off at like 0.4. Looks like a good place to cut off. And we'd have cut this off here, and we'd have made our own clusters, 4 of them. So agglomerative clustering can be helpful when you don't know how many clusters there ought to be. It can be a little bit easier to work with. The silhouette score also works with agglomerative clustering. You do the same thing, get a list of number of clusters. I went from 2 to 10. I'm fitting it with that number of clusters. Fit, predict, and calculating the silhouette score, and when we look at it, we see a big spike at 4, same as we did with k-means, indicating that 4 is the best number of clusters, which we know is the truth. All right, let's move on to anomaly detection. Now, what do you guys think anomaly detection means? Well, an anomaly is something unexpected or surprising. Okay, so in data terms, that means something behaving strangely. It's like it's way outside the distribution of the data, or somehow it's just different, okay? Difference is important. Now, anomaly detection algorithms are commonly used for like cybersecurity or fraud detection, okay? A user that behaves differently from normal users may be a security threat. If the bank thinks you made a purchase that is different from your usual purchases, then they might flag that as fraud. That's what anomaly detection is used for. Now, we're only going to talk about one anomaly detection model, and it's called an isolation forest. It works kind of like a random forest, okay? So it generates a random subset of the data, but this time, instead of selecting rows, it's going to select columns, and then it's going to build a series of decision trees. And the goal for an isolation forest is to figure out the least number of splits it takes to separate an observation from the rest of the data. So if the data is all clumped together, it's going to take a whole lot of splits to rip that data out. But if a data point is kind of far away from the rest of them, then it's not going to take that many splits. And that's how it's going to decide which observations are normal and which ones are anomalies. So here from sklearn.ensemble, I'm importing the isolation forest. I've also imported decision boundary display again from sklearn.inspection. And I've got 2-dimensional data so that we can visualize it with the boundary display. And I'm fitting an isolation forest. Again, this is unsupervised, so there is no Y. It's just model.fit on X. And this is what that particular isolation forest has found on our fake data. So it's like, it thinks here, these green ones are the inliers. These are the normal data points. And these blue ones are the outliers. These are the weirdos that might be wrong. So if you were a fraud prevention guy, then you might look at these blue ones and say, hey, these need to be investigated. These might be fraudulent. These might be a security threat, whatever. Or if you're using an isolation forest as part of a larger, just like machine learning, predictive kind of project, then what you might do is say, these green data points are good. Let's keep them and use them to train our model. These blue points are like weirdo outliers, and we think they're going to skew our model and make our model perform worse. So let's throw out these blue ones and just fit the model on the green ones. The last thing we're going to talk about in unsupervised learning is dimension reduction. So the dimension of your data is the number of columns you have. Technically, it's the number of linearly independent columns you have, but for the most part, your columns are going to be linearly independent, so it's usually just the number of columns you have, okay? And there are several reasons why we might want to reduce the dimension of the data. So under the right circumstances, fewer dimensions can help a model fit faster and better, and it can make a huge difference if you're fitting like a really big model. Say you've got like 1,000 columns, you can imagine that if you only needed to use half of those columns, your model would fit an awful lot faster. But perhaps most often, we're going to use dimension reduction to help us visualize the data. Okay, all of these graphs that we've been looking at so far are two-dimensional. We saw a three-dimensional one once. And the world itself is three-dimensional, and most people struggle to imagine things in more dimensions. People love graphs, but we're really limited visually to at most 3 dimensions, and probably just 2 dimensions most of the time. So we're going to look at 2 different common algorithms for dimension reduction. The first one is called Principal Component Analysis, or PCA. It is the oldest version of dimensionality reduction, at least as far as I know. It can be done by hand. Thankfully, we don't have to because it is a lot of work, but it can be done. And it removes all correlation between the features. You were actually asked to perform PCA in the mini project from last week on linear models. The intuitive idea of PCA is to make a linear combination of the original features that explains the most variance, and then to make another linear combination of the original features that explains like the second most variance, and so on. It's pretty easy to understand when you actually see it, so let's go ahead and see it. So here I've got from sklearn.decomposition, I'm importing PCA, which stands for Principal Component Analysis, and I'm also from sklearn.preprocessing, import standard scaler. You always want to scale the data before you perform PCA. And then we're using a different batch of data. This is from sklearn.datasets. It's called load digits. There's a famous data set used for handwriting analysis, I guess, or detecting handwritten numbers called MNIST. And this is kind of the scikit-learn version of that. So you can see that our data looks like this. This is a 0, this is a 1, this is a 2, this is a 3, this is a 4, this is a 5, this is a 6. They're super low resolution, so it's really hard to tell what they actually are, but it goes all the way to 9, and then it starts over 0, 1, 2, 3, 4. And that's the data we're going to use because it's pretty cool for this purpose. And we're going to check the correlation. Each one of these pictures has 64 pixels. Okay? And so what we're checking is the correlation between pixels. Like this is a white pixel here and this is a white pixel here. So 100% correlation probably. Alright, so this 64 by 64 heat map is showing us the correlation between all the pixels. And as you can see, some of them are pretty correlated, either positively or negatively. This one is like super negatively correlated. This is pixel, what, like 19 by 10, whatever that is. And then if we just plot them, plot the first 2 dimensions, the first 2 pixels, all right? This is what we get. And you can see there's something going on here, right? It doesn't look like a random jumble. For sure it doesn't look like a random jumble. It looks like there is some kind of relationship. Possibly not a linear one, but some kind of relationship. And importantly, a lot of these data points are actually on top of one another. I don't know how big the data set is exactly, but it's thousands and thousands and thousands of dots, and this is not thousands of dots. So a lot of these dots are on top of one another. So here I've got a standard scalar, and I'm doing a fit transform on the data. And then when I'm calling PCA, I leave whiten equals true. Now this whiten equals true is supposed to do standard scaling for you, but it doesn't hurt to just do it twice. It's not an expensive operation. I did it twice to be safe. And then I'm calling PCA.fit_transform on the scaled MNIST data. And now if we look at the correlation heat map, we can see that pretty much all of the correlation is gone. These are all zeros. All of this purple is all zero. As it continues going, it's a little less good, but it's pretty much all zero. And now if we look at that same two-dimensional scatter plot, instead of looking like a whole bunch of things on top of one another like this, it's now in a big jumble. There is no more relationship between the first and second column. First and second pixel. And this is exactly what we want from PCA. We want it to transform things into uncorrelated features like this. So what is this actually doing? Well, whenever you call PCA, I did it on just two-dimensional data to make it easier for us to see, it's going to learn up to the same number of rows or columns that you had. So we have two columns here. So whenever we fit PCA, it's going to find this 2x2 matrix. And when you take this 2x2 matrix and multiply it by the original data, you'll end up with this completely different set of data. So you take the original data, you multiply it by the matrix that comes out of PCA, and you get new data that is uncorrelated, but still contains all of the same information. Another cool thing you can do with PCA is talk about the amount of variance explained. So this is how much variance is captured by each component. You can see that the first few components capture a lot of variance, and as you keep going, there's less and less variance to capture, and so later components capture less variance. But you can also separate this the other way, and you can use this PCA.explained_variance_ratio_, and use the cumulative sum of that to find out how much variance is explained by all of the components up to this point. So here if we start at 1, we got like, 0.1 or something. And then in the first 10 components, there's almost 60% of the variance is explained by the first 10 components. And then if you go all the way to 40 components, then you've ended up with 95% of the variance. So you have 95% of the information in the original data set. The original data set had 64 columns, but you've got 95% of that same information in the first 40 columns. So you can significantly reduce the dimension of the data set without losing very much information. And that's what dimensionality reduction is all about. So here, if we only keep the first 40 components and we look at the correlation, it's not quite zeros, but it's been significantly reduced, I think. And if we plot the first two components next to each other, there we go. Then we see that they're pretty random looking. It just looks like a big clump. It doesn't look like there's any relationship between these two columns whatsoever. Now we're going to do some magic stuff, and we're going to visualize the relationship between the numbers after we've done PCA. So look at this. This is we've only used the first two components. First two components, so they've captured maybe 20% of the data of the variance. When we plot these, color them by the digit that they are, you can see that there's already starting to be some separation. Like, look at these. These are 4s, and they're all in this general area. And this here, these are, 6s, it looks like. And they're all clumped right here. And they've got zeros in between. And it's really interesting, isn't it, that 4 zeros are between 4s and 6s? And then over here, these kind of gold ones, these are 2s. And they're kind of all over in this area. And this, what is this? This is 7s. And they're kind of grouped up here, but they spread out. I just think it's really cool to be able to look at this and see how we're starting to get the numbers separated in a way that, like a support vector machine, could easily draw lines to separate these. And let's compare that. This is the original data before PCA with all the colors, and there's really no splitting up possible here. It's all kind of all mashed together, and there are dots perfectly on top of one another and everything like that. Versus look how much nicer this looks. How much more separation we see. Last thing we're going to talk about here is called T-SNE. This is another dimensionality reduction algorithm. Now, T-SNE stands for T, Distributed Stochastic Neighbor Embedding. I have never heard anybody say all of that out loud. We just call it T-SNE. Now, it uses some pretty cool probabilistic kind of calculations to do something similar to PCA, but the important part, at least for us, is that T-SNE can handle nonlinear transformations, nonlinear information. Okay, so PCA only makes linear combinations of input features. It can only make straight lines. It can only multiply and add, basically. But T-SNE, it makes a lot more interesting nonlinear combinations. Really cool stuff. Sometimes it works a lot better than PCA, and sometimes it doesn't. And in practice, you usually just try them both and see what happens. So to perform T-SNE, you go from sclearn.manifold, import T-SNE, T-S-N-E. Then you fit that. I fit it with 2 components, which I believe is the default. Now you need to scale the data using a standard scaler before you fit the T-SNE. So I've got standard scaler.fit underscore transform the MNIST data, the numbers, and then I'm doing fit transform on the scaled data. And it's taken it down from 64 columns down to 2. And you can see there's no correlation between the 2 columns. This black is perfect 0, and this kind of creamy white color is perfect 1. So there's no correlation between these 2 features. And look at this. Look at the separation that we get just by doing T-SNE one time. Look at this. These are zeros, and they're all by themselves. A support vector classifier could absolutely just draw a circle around this. And what are these? These are 7s? No, these are 6s. And they're all by themselves. And we could easily draw a circle around those. And up here, what is this one? This is 4s, and we could draw a circle. It wouldn't capture all the 4s because there's some over here, but we could draw a circle right here, and we could capture like 90% of the 4s. Oh, what are these? These golden ones. These are 1s, and there's some down here that might be a little harder, but you can see we could draw a circle there, and a circle here, and a circle there, and we would capture all of the 1s, and there'd be a couple of, it looks like 8s in there with the 1s, but man, would we get all the 1s. That's the power of T-SNE. I just find it absolutely incredible. And that's why unsupervised learning is so cool. All right, let's go back to in-person. You just saw 5 unsupervised learning algorithms, okay? 2 clustering, 1 for anomaly detection, and 2 for dimensionality reduction. And how cool was it whenever T-SNE was able to separate those handwritten digits for us? I mean, I'm still amazed every time I see it. This week's mini project is a little bit different. Now, my challenge to you is to do better than I did. The mini project this week is about predicting subjective wine quality judgments based on some characteristics of the wine. This is a well-known machine learning problem, but not necessarily an easy one. Again, my challenge to you is to do better than I did, and my challenge to myself, and I mean I really pushed myself hard here, okay? There's going to be a video popping up right here so you guys can watch me just flail wildly at this problem. But my challenge to myself was to make the best prediction I could using only scikit-learn and giving myself only 1 hour. It turns out 1 hour is like no time at all. So my challenge to you is to do better than I did, and I think a lot of you are going to do it. And when you beat my score, I want you to post a link to your solution in the comments below because I'd love to see what you did. And I'll see you next week.